Welcome from Switzerland. I'm now switching a bit the topic. We are now talking a bit more or going back to the radar topic and actually want to look at what we are scattering off when we look at the meteors. And yeah, just to give you a brief introduction, I'm from the Switzerland University Bern, and what you see in the background is the Jungfraujoch Observatory. And as you see, it's well equipped for astronomy, and it belongs to our institute. So if someone has interest to bring a camera here, it's quite sunny and a good place to conduct these observations. Okay, let's start a bit with the scattering from meteors. We had already some talks in the session about specular observations, and there were also the term mentioned head echo. And this is a summary plot of an observation conducted with an HEPLA radar, where you can see nicely the head echo. This is this faint line here. And the meteor trajectory was long enough that even the specularity was reached and the specular reflection could be seen as well. And this object was large enough to form the so-called non-specular trail. And these are basically the three types of scattering we can observe with a radar. The head echo is confined by a very dense plasma around the meteoroid itself. The specular scattering occurs from the meteoric material that is released during the ablation and forms this ambipolar diffusing plasma column, which we often, what is the typical meteor radars are detecting. And these non-specular trails are in fact very interesting from two aspects. First of all, they do not show up all the time. And secondly, they last by far too long to be explained by diffusion. And one possible explanation why these trails last so long is that the meteors release nanometer-sized dust grains, and these dust grains slow down the electron diffusivity such much that you can keep these trails for seconds or even for minutes, and these trails are blowing away by the wind. And I guess this was also one of these things that if I recall correctly, was seen in the LOFA measurements. When we now go to this specular reflection, and this is what I want to focus now, is when we look on these plasma columns that is left behind when the meteor starts ablating material, then we can bounce back electromagnetic radio waves. Typically in a backscatter configuration, you have one transmitting antenna, some receivers, and you transmit the signal, and it's scattered along from the, let's say, an area of a few Fresnel zones around this so-called specular point. And in that way, this term specular point might be a bit misleading. And this leads to this characteristic signal shape with the sudden rise and this nice exponential decay with this Fresnel oscillations. And this was the picture we had basically known since the last 60 years in the meteor scatter. And we wanted to look a bit more in detail what's going on for this scattering. And when you look into all textbooks, you see an equation like that, what you see here in the right upper corner, where you have that the backscattered power basically is a function from your transmitter, your antenna setup, the wavelength, the classical electron radar cross-section or scattering section, a so-called electron line density, the range, and the so-called Fresnel integrals, which form this nice Cornu spiral shown here. And when you do that, you get a fairly nice match of the measured amplitude morphology and the simulated signal with some properties. However, in this equation, this equation, the right up, did not contain this decay. And this was very often added by simply adding an exponential decay function with a certain decay time, tau. However, this suggests somehow that something is happening to these coefficients. And this is in fact not so truly the case. And what we did now was going back to an old model and solving Maxwell's equation to really investigate why the signal can decay. And you see also some other examples here with a high power large aperture radar. This signal morphology is very often found even to very slow meteors like here. And you see nicely this sudden rise of the signal and this nice exponential decay. And very often one wanted to know this maximum to the best possible extent, because this differs to the magnitude and is also a measure of the mass. So there is a need to get these measurements as precise as possible. And therefore, we went back to a model that was proposed from Polder and Beckerle in 1979. And already this model goes back to some equations from Herlofsen in the 1947. So this is very old thing. And what we basically have is the Maxwell equation for cold unmagnetized plasma. And we express the properties of our scattering function by this kappa coefficient and these omega or the oscillational terms of the electric magnetic field are basically radar dependent properties. And we now make an idealization in that way that we have only a plane wave that has a certain alignment to the trail axis. Could be, for example, perpendicular or transverse, which would match to the H field or magnetic field and the electric field. And we model our trail by an infinite long cylindrical plasma. And the other aspect we are looking, the trail physics is only governed by ambipolar diffusion, which means no electrons get lost by chemical processes. So they remain constant and just spread a radial distance from the meteor trajectory. And when you look at this kappa function, where we basically include the plasma properties, we have for one, the plasma distribution, which is called N, and it provides the plasma density. And we have a parameter from the collision of frequencies, basically as these released meteoric matter and the electrons undergo interactions with the environment atmosphere. And these are modeled here. And one thing I have to note, all computations that were performed on the HPSC Ubelix, which is one of these CERN facilities, and we have quite some computational power, which was a key element here, as some of the computations are very time consuming. When you look to the literature, you find some relation that express the radial spread by the cylindrical diffusion equation, which you find here, where you have an initial trail radius R0 and a diffusion coefficient D, which and the time dependence with how fast this diffusion leads to the spread of the meteor trail. And the analytical solution of cylindrical coordinates would be a Gaussian plasma distribution, which could be expressed in this form, where we have our electron line density and the radial dependence measured perpendicular to the trail axis. And this describes more or less our time evolution of how the electrons are distributed around the trail. Some other studies from Marshall proposed other distributions like a parabolic exponential function, where we try to express this with the same normalization factor. So we have a line density and also a radial expansion. We have a 1/R2 model, which is a bit slower in the diffusion. And this was also proposed in the first study by Marshall. And we have the 1/R/3 distribution, which goes back to a solution from Demand-Oppenheim, who provided DNS simulations of the meteor head ecoplasma, but also for different viewing geometries. And we added this distribution as well. And when we now look what is meant, the meteor is basically flying here at the 0 point towards the screen, and the plasma is spreading radially with a certain distance in meters here. And what you see, these distributions have certain densities directly at the trail axis, with the highest densities in the parabolic exponential and the lowest densities in the 1/R2 model. And the 1/R3 and the Gaussian model are very close together, so that we will not look on those, so these models will only be represented by the Gauss model. The differences are too small. And you have also a gradient, which defines the slope along this plasma model, which is also needed for the simulations. And when we now look at the frequency dependency, it was very well known that depending on your radar setup, the typical decay time, so how long the meteor was seen, depended on frequency. And with this model, we were able to really investigate this for both field components. G defines the reflection coefficient for the electric field component. So this is in the plane of the meteor trajectory, and H is the magnetic field component perpendicular, oscillating to the plasma column. And what you see is there's first of all a distinguished frequency dependency, which is also reflected by the by how fast or how fast the meteor plasma can spread away from the column before the reflection goes down. And we see the higher the frequency of a radar system, the more transparent the signal gets, or the smaller the amplitude is that we can detect. And the lower the frequency, here in 70 megahertz, you see that it's quite or more easy to get a significant reflection at the time. And on the right column, we show the polarization ratio between the magnetic or the transverse scatter and the parallel scatter. And we see that there is quite a difference between both. So basically, it is important to consider the alignment of our transmitted radio wave with the meteor trajectory. We did also look for this for different plasma models. Here it's shown the parabolic exponential model, the Gaussian model, and the 1/R2. As I mentioned, these are the three extremes. And what we see is that the Gaussian model shows this classical shape, what I have shown before. And if we get a more dense plasma, we see a much stronger signal. And we also see a much stronger polarization of the signal. And when we use the 1/R/2, we see basically a strong scattering over a wide range of radius, in particular for the higher densities here above 10 to the power of 13, and almost no polarization dependency anymore. We tried in the following, we will also only look at the Gauss model, but mainly as we wanted to show that the analytical solution, which is given by the Gauss model, could be really seen for some meteors, and that we can actually really use these reflection coefficients to describe the meteor signals. However, we have also to clearly say it is also possible in some cases to use the 1/R/2, and certainly it's also possible with the 1/R/3. When we now look at a profile, then we have to, we will see that there is this transition between overdense and underdense regime. And this is basically in one of these equations that we have a singularity by this term here, where we divide basically by kappa. And when this complex function gets close to 0, which happens at the transition between the underdense and overdense regime, then we have a singularity, and this singularity leads to a resonance effect in the perpendicular or transverse scatter case for certain line densities. And we see that these line densities already also geometry dependent. So for the parallel case, we will not see such an overdense transition. And you see that the signal morphology would be quite different. These resonances can be quite intense. We have here a factor of 5 amplification over the parallel case, or here a bit weaker. We did also investigate in more detail the collision frequencies, which are basically an atmospheric property. So these collision frequencies are altitude dependent and also from the background plasma density dependent. So for example, a person that is causing or forming a trail higher up will undergo different collision frequencies than slower meteor forming a trail at 80 kilometers. So there is an atmospheric dependency of these collisions, and at the end, these collisions define how strong these resonances can evolve. We also looked for the magnetic field dependency in the way that the electronic component can be already magnetized, whereas the ionic component remains unmagnetized due to the collisions. And what we can say here and show in this plot is that basically for the dense plasma column that we can detect, this is not a big issue. Only for the background or for the ambient electron densities in the D and E layer, this could be something worth to consider, as the electrons are already magnetized, but within the meteoric plasma where we do have most of the observations, this is not a big issue. And we just wanted to test this here and to understand how much this would affect us, because there are some previous studies from Kaiser et al. They looked at the alignment of trails and how with the magnetic field lines and whether the diffusion could depend on this alignment. And this study suggests some case, but for most of the observations that we performed, this was not an issue, and this is basically confirmed by this plot. Okay. Now, as I mentioned, there was quite some difference between the two scattering regimes. And when we have a radar, we basically can have two cases. We can have a circular polarization or a linear polarization. Many of the old systems use a linear polarization. This would mean that we should see a quite strong difference between the polarization that is transmitted and the trail alignment towards this polarization. And when we look now to this plot up here, there you see a delta angle, and this delta angle defines basically the plane where our electric field is oscillating compared to the trajectory of the meteor. The parallel case defines an electric field oscillating in the y-plane and a trail alignment in the which is parallel to the y-plane as well, where the transverse case, which denotes here as a delta angle of 90 degrees, would be the opposite case. Basically, the incident radio wave is oscillating perpendicular to a meteor trail aligned with the y-plane. And when you now look to this left upper panel, you see how the signal amplitude gets much stronger when we get to this perpendicular observing geometry compared to the parallel case. The lower panel shows a summary of that for the different frequencies. So this effect is in all frequency dependent or visible, and clearly from the observation geometry dependent. We now were able with the CMOS system, because there we have the time of flight information, we have a well-defined trajectory information from this multistatic configuration to select cases where we have transverse scatter within 2 to 3 degrees to this perfect 90-degree difference between the transmitted electromagnetic wave and the trail trajectory, and the parallel case as well. And what you can see is for these 4 examples here, that the black crosses denote the measurements, and the red line shows our reflection coefficients, which were manually fitted for all 3 frequencies to these observations. And we have here an example that we compare for 92 kilometers in at the upper 2 panels, and for 86 kilometers in the lower 2 panels. And indeed, what we see is that the lifetime or the decay time of the signal is quite different between the parallel case and the transverse case. But when we fit our diffusion coefficients, we see that they are quite similar. So there is a high consistency. However, this also means that without knowing that, it's not trivial to get from the decay time alone a proper estimate of the diffusion coefficient. And it also is quite a difference between the signal magnitude, as also the Q value is quite different between these transverse and parallel cases, which is shown here a bit for the lower case, where we have here an amplitude of the backscattered power of the order of 5, whereas we here have only 2. And when you look at the electron line densities, then you see that the parallel case had a much higher line density compared to the transverse scatter case. And this also indicates that this transverse scattering regime or scattering regime is much more efficient and easier to detect than the parallel case.
Gunter, you have 3 minutes left.
Yeah, and basically the equation now gets from the backscattered power expressed by this reflection coefficient G for these different geometries, and only depends on this, again, radar parameters. We also looked at the altitude dependency and for the diffusion and initial trail radius, and we see that the initial trail radius has some altitude dependence between, let's say, 50 centimeter to 1.5 meter, but it does not scale with the mean free path, which was a bit speculated before. And it fits, our observations fit quite well to previous studies from Campbell-Brown. And for the diffusion coefficient, we see in the transverse scatter scale that they are a bit higher compared to previous studies. And we are still trying to understand it a bit more. And what is also very evident is that there is quite some scattering around these lines. And this disappears a bit when we look at the parallel case. And one reason why we think is this the case is in the parallel case, we don't have to deal with these resonances and with these collision frequencies, which is basically a free parameter. And that's why we expect less variability there. And indeed, we found it's quite different between 2 cases. Okay, basically with this full wave scattering model, we can describe the scattering process also for forward scatter or for more different geometries. And we have all 4 plasma models ready. including the one from Jakob Demand, and which closely resembles the Gaussian model. And this is very good because we could at least show that some meteors can be fitted with this analytical solution. And but we also have clearly to say, as soon as meteors start to behave very different from single body ablation due to fragmentation, the whole thing gets much more complicated, and certainly also chemistry plays at some time a role in these plasma distributions. And this is some future work, I would say, but at least we were able with the CMO data to confirm that the model that was developed by Polder and Beckerle original nicely could be observationally confirmed. Yeah, thank you very much.